Okay, this is the second example of performing element reduction in order to, in this case, solve for a circuit parameter. Specifically with a voltage Vx from this node to this node, which happens to be across this entire resistor network. So in this case, I've provided some voltage and current sources to drive this circuit, rather than just providing the load. So we see we have a couple voltage sources in series and a couple of current sources in parallel, and this kind of scary looking resistor network. It's only scary looking because I've actually drawn this such that I've got wires crossing over one another. So anytime you see the point, the dot, it means we have a connection. But if we see this little loop or wires going over one another, that means they are not connected. Okay, so let's start by trying to reduce some things that we know. For example, we see right away we have these voltage sources that are in series. Voltage sources sum in series. So if we want to reduce that to a single equivalent value, for example, from here to here, we're going to lose -5, so that's like gaining 5 volts, and then gain 10 volts. So it's equivalent to 15 volts from the lower terminal to the top terminal. Again, from here to here you lose, because of this polarity, whatever the value is out front. So we lose -5, that's like gaining positive 5 volts, and then we gain the value out here, it's 10 volts. So the sum is 15 volts. And we also see these current sources are in parallel with one another. So if we want to draw an equivalent current with current going up, that's going to be equivalent to 300 going up minus 100 going down, or 200 milliamps. It's kind of like doing a KCL at the top node. Okay. Likewise, doing these voltage source combinations like doing KVL. We can walk around this artificial loop we've created. Plus 15 minus 10 plus -5. Okay, so we can combine those sources pretty quickly. Now let's concentrate on this resistor network, because the goal here is to find voltage Vx. We could find that by just performing KCL and KVL analysis like we have been doing in the past, or we could find the equivalent resistor between the two voltage terminals that we're interested in. And once we know a single equivalent resistance value, all we need is the current through that resistor in order to solve this problem, which happens to be 200 milliamps. We've already figured out. So let's go ahead and start by labeling this thing, just like we did in the last problem. I'm going to call this top node A, bottom node B. We're going to label all other nodes. So we've got a node C here. Caution, make sure you propagate these wires. So this is actually node C down there too, and all this is C. Okay, so this is node C down here as well. Okay, we've got, say, node D right here, and this is another wire. We've got to propagate all wires. Goes all the way over here, connects to these guys. So this is also node D. And then down here we see a node, but that's connected to B, so this is all single node B. Okay, it turns out this thing's not quite as complicated, right? We've only got 4 nodes, A, B, C, and D. They're just kind of split up. Okay, so let's redraw the equivalent resistance seen from A to B. I like to use the method I showed in the last video. You can, if you identify things in series or parallel, you could use the method of erasing those values on your chart. So if you do it in pencil or whatever, and replacing those parallel resistors with equivalent resistance and the series resistors with an equivalent resistance, and continue to do that until you reduce it down. I personally just don't like that method because you're erasing and writing, and if you make a mistake, it's hard to recover unless you're computing the equation as you go and provide that information. It's hard to debug it. Okay, so node A goes straight into a 30 ohm resistor, at which point we hit node C. Let's cross that one out. Node C, there's 1 branch, 2 branches, 3, 4, 5 branches coming out of C. Don't forget that node where we cross over a wire. So I'm going to draw C with a split into 5 branches. Okay, I've got C to D through a 3K ohm. Cross it out. I've got C to D through a 1.8K ohm. That's D. That's D. Cross it out. I've got C to D through a 900 ohm. Cross it out. I've got C to B through a 2K. Another C to B through a 2K. So the last two are 2K ohm each. Both of those going to node B, which would be our endpoint. So I can connect the node B's together, and I can connect all these node D's together. Okay, cross those out. Okay, so we got rid of a lot of them right there. So the one where we ended up in B, the bottom path here, we're done, but we haven't finished over here. We still got to get to B. Okay, so D is this node highlighted in blue. How many do we have coming out of that? Oops, I made a mistake and crossed out the wrong one over here. I got to cross this 2K ohm out, and this 1.2K is still active. Okay, so I've still got 1 and 2 resistors coming out of node D. So I'm going to draw a split into 2. One of those is a 600 ohm going to node B. The other is the 1.2K ohm going to B, right there. And we're done. So we can connect those up, connect those bottom together, and we're done. Okay, so now we can just make some resistor combinations here. Right away we see that the 600 and 1.2K are in parallel, which is 400 ohms. We see the 2K in parallel 2K here on the bottom, which will be 1 kilo ohm. And we see the 900, 1.8 kilo ohm, and 3 kilo ohm in parallel, which is 500 ohms. Okay, so let's redraw this. A goes to 30 ohms, and now we actually only have a split into 2, this equivalent resistance and this equivalent resistance. Top one is 500 ohms, bottom one is 1 kilo ohm. 500 ohms goes to D, which is going to then be in series with a 400 ohm. And we connect those together, and that's what we called node B. Alright, so now we have this 500 in series with a 400, so that's 900 ohms, in parallel with 1 kilo ohm, which is 473.7 ohms. And then we see that we've got a 30 ohm in series with that 473.7 ohms to B. Therefore, the equivalent resistance between A and B is 503.7 ohms. Okay, so redrawing our equivalent circuit, we found that we have a 200 milliamp current source going from bottom to top. We have a voltage source that's 15 volts, and a resistor That is 503.7 ohms, at which we have voltage Vx across it. So to solve this, we need the current through this resistor. Conveniently, we have a current source that is in series with this resistor, so we know that the current through the resistor must be the same as the current through the current source, which is 200 milliamps. Okay. Therefore, Vx can be expressed simply as the I through the equivalent resistance times the equivalent resistance, which is 200 milliamps times 503.7 ohms. Therefore, Vx is equal to 100.7 volts.